Well, welcome everybody to the WTB Shack here in Franklin, Tennessee. We're going to be doing the presentation that is for the October meeting of Williamson County ARES in Franklin, Tennessee, Middle Tennessee, for those who might be watching elsewhere. And before I get started, I want to give some credit to Don Johnson, N4DJ of Williamsburg, Virginia, who introduced me to antenna modeling. And for Yulia, and I don't have Yulia's last name, but you're going to see a video in just a few moments, and Yulia is the star of it, and it introduces fractal mathematics and applies that to antennas. And fractal mathematics is something that was only created as a theoretical concept in 1975. And a lot of us at Williamson County ARES and the ham radio community in general went to high school early enough that we never even heard about it. But this will give you a little bit of a theoretical background about what fractals are, and you'll see that applied to antennas. It's about a 4-minute video, and Yulia will begin now.
Science! Out loud.
What do snowflakes and cell phones have in common? The answer is never-ending patterns called fractals. Let me draw a snowflake. I'll start with an equilateral triangle. Then I'll draw another equilateral triangle on the middle of each side. I'll pull out the middle and repeat the process, this time with 1, 2, 3, 4 times 3, which is 12 sides. If I do this over and over, the shape will look something like this. This is called a Koch snowflake, and it has a special property. No matter where I look or how much I zoom in, I will see the same pattern over and over. Never-ending patterns like this, that on any scale, on any level of zoom look roughly the same, are called fractals. We can actually draw a Koch snowflake on the computer by having it repeatedly graph a mathematical equation. Each time we add a triangle, one side of the Koch snowflake will turn into 4. After the first repetition, we'll get 3 times 4 to the first, or 12 sides. After the second repetition, we'll get 3 times 4 to the second, or 48 sides. After repetition number n, we'll have 3 times 4 to the n sides. If we do this an infinite number of times, we'll get infinitely many sides, so the perimeter of the Koch snowflake will be infinite. But the area of the Koch snowflake wouldn't be infinite. If I draw a circle with a finite area around the snowflake, it will fit completely inside, no matter how many times we increase the number of sides. So the Koch fractal has an infinite perimeter, but a finite area. In the 1990s, a radio astronomer named Nathan Cohen used the fractal antenna to rethink wireless communications. At the time, Cohen's landlord wouldn't let him put a radio antenna on his roof, so Cohen decided to make a more compact, fractal-like radio antenna instead. But it didn't just hide the antenna from his landlord, it also seemed to work better than the regular ones. Regular antennas have to be cut for one type of signal, and they usually work best when their lengths are certain multiples of their signal's wavelength. So, FM radio antennas can only pick up FM radio stations, TV antennas can only pick up TV channels, and so on. But fractal antennas are different. As the fractal repeats itself more and more, the fractal antenna can pick up more and more signals, not just one. And because the perimeter of the Koch snowflake grows way faster than its area, the fractal antenna only takes up a quarter of the usual space. But Cohen didn't stop there. He designed a new antenna, this time using a fractal called the Menger sponge. The Menger sponge is kind of like a 3D version of the Koch snowflake. It has infinite surface area, but finite volume. The Menger sponge is sometimes used in cell phone antennas. It can receive all kinds of signals while taking up even less area than a Koch snowflake. Now, these antennas aren't perfect. They're smaller, but they're also very intricate, so they're harder and more expensive to make. And although fractal antennas can receive many different types of signals, they can't always receive each signal as well as an antenna that was cut for it. Cohen's invention was not the first application of fractals. Nature has been doing it forever, and not just with snowflakes. You can see fractals in river systems, lightning bolts, seashells, and even whole galaxies. So many natural systems previously thought off limits to mathematicians can now be explained in terms of fractals. And by applying nature's best practices, we can then solve real-world problems. Fractal research is changing fields such as biology. For example, MIT scientists discovered that chromatin is a fractal and that keeps DNA from getting tangled. Low Look around you. What beautiful patterns do you see? Hi, I'm Yulia. Thanks for watching Science Out Loud. Check out these other awesome videos and visit our website.
Okay, back to the beginning again. I'm Ted, W3TB. We all know each other pretty much here in the room. Hello to anybody who's watching because we stream this as well. And this is a presentation about modeling antennas on your computer using EZNEC 6.0. And I'll just say briefly that there is a new version of EZNEC 7.0, and it's free for download off the internet. And if you want to start modeling antennas, just go to 7.0 right from the beginning. I used 6.0 to create this. Here's what we're going to be doing. We're going to model an antenna using EZNEC 6.0. And I've got it here on the computer where all my slides are. And then we'll do a lot of tests and adjustments to it. And having done that, we'll take the antenna modeling, which is going to be an ordinary dipole, and show two other ways to model it. And then we'll talk about fractal antennas and dipoles made that way as well. And there would be question time at the end. Modeling antennas on your computer. I've been doing this for about 14 years, I guess, using EZNEC 6.0, and now 7.0 is available. By the way, if you want to find that, is at EZNEC.com. You can just download it for free, turn it on, it's ready to go. Once you know what you're doing, it gets to be a simple program to use. There is another modeling program that I also use called mmana.gal, and it's not an American program, which means it's got a lot of great features, but it's metric. And if you like to use metric, that's great. But it's difficult for Americans who really weren't educated particularly well in metric. And then the other difficulty with it is that this modeling work uses the X, Y, and Z dimensions that we all learned to graph out when we were kids in about 9th grade in algebra. And in that one, the x-axis goes left and right, and the y-axis goes up and down, and the vertical axis is lifted vertically off of that. But the mmana.gal goes opposite. It takes the x-axis up and down and the y-axis left and right, which isn't particularly a problem as long as you really pay attention to it and don't get confused being an American ham who learned that x goes left and right and y goes up and down. So we'll move on from that. The program also includes a lot of pre-made models that you can then adapt to change bands, change your use of them, change your sizes, a lot of things you can do. We're going to start with one of those, and we're going to go through a series of steps. One of those steps, which is probably really important, let me turn around where I put it, is to make a little drawing of what you're doing so you don't confuse yourself and you've got it clear in your mind. I made this little drawing, the dipole, and below it is an inverted V dipole. And we all know dipoles, but it's still good to actually stop and do that. You save yourself a lot of heartache and trouble. The antenna is going to be made out of what we're going to call wires, even though you may find that you want to do a beam or something made out of tubes or other kind of construction materials. We just call them all wires. And then within the wires definitions, you can change their size to make them anything you want to. Then we're going to load a source of a feed point onto the antenna. It'll be called source instead of feed point. And then we're going to test it, decide whether we like it, try it again, make adjustments, play with it until we actually have what we want to have. And antenna modeling can be great play. You can almost think of it as a computer game if you want to. And my screen just went dark. There we are. And when you're done, you can do a save as, save it. There's a little place you can write a note to yourself so that you remember some other day when you open up the program what you did and why you did it. Very, very handy. So it begins with this. I call it the table of contents page. And it reads like the table of contents in a book. It takes you to places where you can make all manner of adjustments and creative things to your antenna, and then save them and keep on going. And we'll start at the table of contents page, go off to do an errand, and come back to it again. Like this one, for instance. This one is called, the name of it actually, it's at the top of it. On the table of contents page, by the way, you'll see little arrows pointing to the right. Any one of those things with little arrows is a function you can open up and do. So we're going to go to this one, and this is where I get a list of antenna models that are already in there. And I chose the one called BY dipole. BY just stands for backyard. It's nothing elegant about it. It's the kind of dipole you'd put up in your backyard. It's the one we're going to use. The BYV below it is an inverted V dipole. And there are a lot of others that are on the screen. But these are good ones for us to use because just about everybody has built a dipole and knows what they are and how to use them. So the purple arrow there points to the BY dipole, and that's what we're going to use. Then we go back to it, and look at that. Across the top, I changed the name, and I called it backyard dipole, just so that BY is clear. We go to the title box, and I changed it to WCares Demo Dipole number 1, just so I remember what it is. And having done that, I hit OK, and it takes me right back to the table of contents page. Excuse me. The table of contents page is a really, really handy thing. And I recommend not opening more than one of these functions at a time, because if you get too many on your screen, you'll confuse yourself. And I find I don't like to be confused. Perhaps you don't either, because I'm so much like that great British philosopher and psychologist. You all know him well. You all read the stuff about him when you were a kid, and that is Winnie the Pooh. And Winnie the Pooh said about himself, "I am just a simple bear of small brain." I am just a simple bear of small brain. I understand that. So just don't confuse yourself by having too much going on at the same time when you're working on an antenna. You'll save yourself a lot of trouble and heartache. Let's get back here again. I'm going to work down the lines of the table of contents box and go to the one called frequency, which is right at the top there. And this one says 14 megahertz. This dipole that somebody put up there as a model is a 20-meter dipole. Garden variety, standard, backyard variety, 20-meter dipole. If you look at the box, you'll see that it says 14, the frequency. And if you look to the right of it, where I put a little arrow, there's a box called rescale. You could set up in the number of that box something other than 14. Say you wanted to make a 40-meter dipole, you'd put 7. Click on the rescale box and it'll reproportion the whole thing for you, so you don't have to sit there and fiddle with it that much. Then hit OK, and you're done with that box. The next box I want to open is the one called wires. And if you look at this one, it has one wire. And that wire starts where X and Y equals 0. That is to say, the very middle of the X and Y scale. And where the Z says 30, it puts it 30 feet in the air. And then it goes to wire number 2. And wire number 2 is still where X equals 0, so it hasn't moved left or right. But on the Y scale, it's gone out 33.43 feet. So we've created a wire 33.43 feet long. And since Z still says 30, it's now suspended 30 feet in the air. Pretty simple stuff. All the wires are created with their ends defined. We defined one end, we defined the other end, and it's stretched between them. And that's how you make a wire. On this one, let me point out that further over there where there's an arrow, where it says segments, the way this program really works is to calculate radio frequency current at locations across the wire, and they call them segments. So since we have 11 segments on this one, there's 11 places where current will be calculated when we run the model. Note that it's an odd number. I want to, in my next function I'm going to do here where it says source, I'm going to identify the feed point of the antenna. And if you need to feed an antenna at the middle, make sure your segments is an odd number, which means there will be a segment right in the middle. Okay? Important to put a segment right in the middle. Otherwise, when you try to feed the antenna at the middle, it won't allow it. And we're going to see that in just a few moments. Up at the tops, also look where it says Show Insulation. If you make an antenna with insulation wire, insulated wire has a slightly lower, not much, but a slightly lower velocity factor than non-insulated wire. So since we all run off to our big box hardware store and we buy THHN stranded 14 or whatever we like to make antennas out of, it's probably, if you're going to make an insulated antenna, good to have that box checked. This one came that way because the person who created the master model that we're playing with did that. So we'll move on to the next thing. This is the sources box. They call it sources, but this is really the feed point of your antenna. And we're trying to feed this dipole in the middle. If you look at this, it's wire number 1, and it shows where the specified position would be. On wire number 1, I'm feeding it at 50%, which is to say the middle of the wire. And it will allow for that, where the next box says actual position says 50%. And why? Because I had an odd number of segments. It won't do that if you have an even number of segments. I found that out the hard way when I was first learning how to do this. Amplitude is 1, that is to say the whole of the amplitude. And so we've done that one. We go back to the table of contents box. And in the table of contents box, kind of ignore that noise. We have an audience today, which is my dog. Her name is Maddie. So you see where it says loads, transmission lines, transformers, L networks, and Y parameter networks. Those are all things you can do. We're not going to do them because we're working a simple dipole, but they work the same way. You click them, you open up, you make your change, and you go back. I want to go then down to the one that says ground type and ground description. And if you click on those, you get, this is both boxes, by the way. Ground type says on the left, it's clicked for real. It also allows for perfect and free space grounds. Perfect grounds, do any of you have perfect grounds? I doubt it. You probably only want to click that box if you're stringing wire over a saltwater marsh or something that's really conductive like that. Free space, if you're building something like a VHF or UHF antenna, it's going to be up on a mast or a tower and it's way up high in the air, pretty far separated from the ground, then you could use free space because the ground hasn't got much to do with an antenna that's many wavelengths above the ground. Then off to the right side is ground conductivity, and the one that was made on this one as it 0.0303 for ground conductivity. Ground conductivity varies everywhere around the country. So you can go to the internet and you can get a map up that'll show you what your ground conductivity is in your part of the country. For Tennessee, probably 0.04 is a good number. 0.03 is not very far off of that, so you can probably leave it alone. But there are parts of the country where the ground differs dramatically from the normal ground that we have here in Tennessee, and that's where you would change it. In both cases, you click OK, and it'll take you back to the table of contents page. Then when you go down to plot type, which is further down that page, this will give you, when you run the program, it will give you azimuthal plots, which is left and right directional. It'll give you vertical plots, which is above the horizon. And it will give you something called a three-dimensional plot. And I'll show you one of those in a few minutes. It's pretty difficult to look at and make sense of it, but it'll take all the plots and put them in a three-dimensional diagram, and you can see what it looks like three-dimensional. Now look at the box on the right. You can specify for the vertical measure, the vertical plot, to not have it on the strongest element of the azimuthal plot, which is to say, if you wanted to steer your vertical plot and look left or right of the strongest part of the azimuthal plot, you can do that. Specify how many degrees, left or right, minus or plus degrees. I'll show you what you might have done with that, I'm not going to do anything with it, but what you might have done with that when we get to actually putting the plots of this antenna on the screen. But that's where it is, and I'll refer to that later. Now we're back to the table of contents page. And I want to point out just a few things down there. About 2/3 of the way down it says units. This model that we opened up and we're working with measures lengths in feet. It'll also measure inches if you wanted to do that, and you might want to do that for a UHF or VHF antenna. It will also allow you to do metric measure, and with metric measure you could measure it in meters or in centimeters. It will also allow you to do it in wavelengths. But that's how you do that. You go there and just change what you're trying to measure. Come down further and see that the third from the bottom says alternate SWR ZO, which is to say impedance. When we get into looking at things later on, we could actually look at different impedances on the antenna. Right now it says alternate SWR measured at 75 ohms. The coaxes we use are mostly 50 ohms, the RG8, RG8X, RG213, LMR 400, kind of 50 ohm coaxes, and that's normally the standard for how we're going to be measuring SWR, but it allows an alternate. You can choose the alternate one. Right now it's set 75 ohms. When I did the program last year about, excuse me, the program last year about off-center fed Windows, I was wanting to feed antennas at 200 ohms. So I just opened up this function and changed it to 200 so I could see what the SWR was at 200 ohms. Because I was feeding those antennas with a 50 ohm coax through a 4-to-1 current balun, which means I was looking at the other side of the balun for 200 ohms. That's the way they did it and how I did it. Let's continue on here then. Oh, let me go. What you see on the left side, those little boxes, is just another set of functions you can do. We did opening to find this antenna, find our way through the folders to the antenna models that it comes with, the dipole that we're using. The next one is the save as. It's just like any other computing you do where you save your work as another file name at the end. And then the third one down is antenna notes, where you would open that up to write a note to yourself about what you did and why you did it. So later on when you look at it, you don't come around and say, why did I do that? You know, leave yourself a note. You'll save yourself a lot of heartache when you look at your model later on. Then coming down that, I'm going to skip through most of those, but the ones I want to point out near the bottom are SWR, view antenna, and all by itself at the bottom, FF plot, which stands for far field plot. That's where we're going to see visually what the antenna is actually doing. First one let's go to is the view antenna. Look at that thing. You can see carefully that the green wire is the wire we described, the one that's 33.43 feet long, starting where x and y equals 0, that's to say the middle, and going up over the wire axis for 33.43 feet, and it is 30 feet up in the air because that's what we specified for Z. There it is, just like it looks like. Guess what? We can go back to our paper diagram and say, yes, we got it right. That's very helpful. Looks also red in the middle, right in the middle is a red circle. That's the feed point. And notice the number 1 because it's wire number 1. Pretty simple and straightforward. Look to the upper left of that where under the word zoom there are 2 sliders. I'm going to show you later the slider on the right, which will only work after we've actually modeled the antenna. But it's the place where you can change the proportion of the arc that will show you where current is flowing on the antenna. The other thing you can do with this is to take your cursor off your computer and place it on the antenna, and you can turn around and look at it from any other dimension or direction or angle you want to, just by moving it around. Okay, we'll go on. This is the one called SWR. And if you look at the left of the boxes, it'll put places where you specify a scan range. Now you don't have to, one of the nice things you don't have to worry about is you can operate out of band with this thing. 20 meters is 14.0 to 14.35, as we can all know. But when I set this up for this scan, I went below the band and above the band to scan wider. I set it up to scan from 13.8 to 14.5 megahertz, both ends outside of the band. And then the third block down is how many kilohertz do you want to have each of the frequency scans done, because what this is going to do, it's going to scan the wire at every segment that we defined in the wire section and at every frequency interval that we set up. I set 0.025, which is to say 25 kilohertz. Every 25 kilohertz, it's going to scan all the segments and produce a graph like you see on the right. And that is a standard SWR graph, like you've seen these things before. All the dotted lines going vertically are the 25 kilohertz intervals. And it starts at 13.8, scans all 25 kilohertz intervals all the way up to 14.5. And it produces that graph of the SWR change with frequency. And then down below it, where all those numbers are, you'll see it's measuring at 13.8 outside the band. The SWR is pretty high outside the band there at nearly 3 to 1. It says 2.93. And then down below it, it will give you the impedance, 100.8 ohms at that frequency. You can take your cursor and move it to any of those vertical lines you want to, and it will change all the numbers to show what's true at the frequency you selected. I didn't do that. It's still set at 13.8, but you can read all of those things. And then on the right side, it says ZO at 50 ohms. That's measured on 50 ohm coax. Look at the upper left of that box, and you can see that I've checked 50 ohms, but I could just as easily have checked 75 ohms and see what it reads with 50 ohm coax. I'm going to do that later on. Let's go on here. Now, what happened when I looked at that SWR plot? It's best at the top end of the band. The top end of the band is going out of the band all the way to 14.5. This is not really very good. How do you solve a problem when your SWR, best SWR situation on a band is too high for you? Well, you lengthen the wire. So let's lengthen the wire. It had started at 33.43 feet. I lengthened it to 34 feet, a little bit more than 6 inches, a little bit more than a half a foot. You see that on end number 2, Y is now set at 34. And we go back and we run the SWR function again. And you see that that curve of the SWR minimum has gotten a little bit better and found its way towards the middle of the band. Now, I'm a CW guy, so I would like it to be even lower. I'm not going to do that right now in here, but what if I went and opened that up to 34.1 feet or 34.2 feet? It would move the SWR minimum further to the left on the graph, down towards the CW portion of the band, which might be just exactly what you want if you're a CW operator like me, or you want to run RIDI, or you want to run FT8 at 14.074 is where FT8 is. That might be what you want to do. You could do this a second time. You can do this as often as you want to about the length of that wire. I'm going to leave it at 34. And look at that, what the second of the right side of this does. There I clicked 75 ohm instead of 50 ohm coax, and the SWR got a lot better. If you look at the numbers on the one on the left, it says 1.7 at 14.2 megahertz, because I clicked the 14.2 megahertz vertical dotted line. And so I got all the numbers for there. 1.7. 1.7 is not a bad SWR. We can all live at less than 2. But 1.7, and you can do a very coarse, imperfect, but approximation of SWR by dividing together and proportioning and seeing what you get between the impedance of the coax feed and the impedance of the antenna. In this case, it says 84.9, 85 ohms. 85 divided by 50 will get you like 1.7. There's the SWR. You go to the one on the right, 85 divided by 75 ohms will get you a much, much lower SWR. 1.13 is what it says here. That's not a perfect way to calculate SWR, but it'll get you close, and it'll tell you what's going on. I have to admit that I have made many, many antennas, and the coax I put on it is what's convenient at hand, and I stick it there, and it works up, and the SWR is okay, and I work stations and don't worry about it very much. But look how revealing this is about using the right coax. This is a 75 ohm antenna approximately, and I fed it with 75 ohm coax in the right block, and look how much better the SWR is. I should pay attention to my own teaching on that. So let's go back further. This one going down to the far field plot. That's the bottom of those boxes. Far field plot. If we do the far field plotting and see what we get graphs. The one on the left is the directional graph, the azimuthal graph of this antenna, and it is exactly what you'd expect it to be. The wire is up and down the y-axis, which lets us think of it as a north-south wire. It's going to have its best performance directly off the side, so look at that great big loop going east and west, just like it ought to be, and we get largely what we intended to get. If you look at this, it says that the antenna as a function here is at 6.26 dBi. 6.26 dB better than isotropic. And that's pretty good for a dipole. Okay, I'm a contester, you know that. Former president of Tennessee Contest Group. And what I did on this graph was to place little icons for Europe there to the northeast and South America there to the southeast, because the center line from here to Europe is 45 degrees to the northeast, azimuth, and the center line to the body of South America is 135 degrees to the southeast. And as you can see, they are not on the fullest body of the antenna's pattern. Now, back when I was talking about azimuth and elevation a few minutes ago, I showed how you could put a number in to steer the vertical aspect of the measure to where you wanted it to be. You could have put in minus 0.45 degrees and it would measure the vertical pattern towards Europe, or plus 0.45 and towards South America. But in this case, I didn't do it. But you can see that. Now, one of the things that's really important about when you're looking at antennas like this, and you can see this in the magazines and in the books about antennas you will read, is they will talk about beam width. And when they do that, they are telling about how wide is the pattern when it is 3 dB less than its best. You see on this case, the strongest signal is due east. And if you look basically on the piece towards Europe, just for instance, you'll see a dotted line that goes on here where it would show where minus 5 dB is. It's better than minus 5 dB. It's about minus 3 dB towards Europe and about minus 3 dB towards South America. The ads will specify beam width as 3 degree width left and right of the center. In this case, 3 dB towards Europe, you lost 3 dB. 3 dB is a half an S unit. You can just barely hear that. So it's not a bad pattern. If you look at this thing, it will also show that the beam width is 41.6, not actually 45 degrees. But you can see it's approximately 45 degrees. 41.6, double that one, and now you have the beam width of this antenna. Let me also point out that the outer ring of the one on the left is at 6.26 dBi. The outer ring on the one on the right is at 6.83 dBi. And there's about a half of a dB difference between the inner ring and the outer ring. And the reason for that is easily seen on the graph where it meets the outer ring and there's a green dot. See that green dot? When I was setting up, I think I didn't mention this when I went past that earlier. Let me, in my mind, go back. When I was choosing between whether to go to azimuth or elevation, if I go to azimuth, it will not actually measure azimuth at the horizon. There's really no signal going out at the horizon. All of our signals go up at some kind of an angle to come down at some sort of an angle where they propagate to. And I chose 25 degrees. Most of the X's worked between about 15 to 20 and about 35 to 40 degrees off the horizon. I chose 25 degrees arbitrarily. That's fine, and you see that on the left graph. But if you look at the one on the right, which is the vertical graph, see that green dot? It's not at 25 degrees. Each of those little ticks marking up the edge of that arc is 5 degrees. So the best signal is actually not where I set up the model to read it. I set it up for 25 degrees, the best is at 33 degrees. See the difference? That's why the right arc is at 6.83 and the left one is at 6.26. And that's what caused that and why it happened. You can change the best angle vertically by varying the height of the antenna. You could put it higher and the angle would get lower. But it's good to see the difference. So let's go back here further. That one, that little nightmare, is the one that was called a three-dimensional. If you can make sense of that, have fun with it. You could put the little cursor on there, turn it around, look at the three-dimensional pattern of this antenna from different angles, if you want to do that. And then I go back here to the plot, and I took that slider that was on the left where the purple arrow is, and I raised it a little bit higher and produced over the representation of the antenna, I produced an arc, a frown-shaped arc, that is representative of current flowing on the antenna. If you remember back to the presentation I did on off-center fed antennas, we had to stop and review, let's do it again now, a concept that we all learned back at the beginning and really never talk about it anymore and really don't use until you're doing an antenna modeling here, and that is the concept that power on an antenna like this is equally strong everywhere in the antenna. But remember the pi formula, P equals IE, power equals intensity times electric motive force, or that is to say amps times current, amps times volts. On an antenna like this, power is equally distributed, but voltage near the ends, where the insulators are, is high and current is low. A quarter wavelength away, back at the middle of a half-wave dipole, current is now high and voltage is now low, which is why we feed dipoles at the middle and why they work so well. This is going to represent current flow. The one on the right there, I just decided for fun and play to model this antenna, the same one, at 15 meters, 21 megahertz, and look what we got. Voltage is still high, current is still low at the insulators at the end, but since the middle is not a quarter wavelength from the end like it is on 20 meters, the current has started to go down. It's still pretty high. That means voltage has started to come up. That means an SWR situation is created, and that's a good thing to learn about this antenna. Still, look at the antenna. It's the green line. The circle in the middle of it, the red circle in the middle, is the feed point. We can finish with that one. Now I want to go through two alternative ways of modeling the same dipole. The one we started with was a single wire starting where x and y equals 0 at 30 feet in the air, going out to 34 feet, that's where I changed it to, also 40 feet in the air, a single wire. What I'm going to do is change it to make it two wires, which is how we'd actually build a dipole anyway, isn't it? And since 34 feet seemed to be the number to use, half of that is 17 feet. We're going to make a dipole that is the same length, but each side is 34 feet. And then I'm going to go with another dipole here where I'm going to do what looks like a little bit of a trick, but it actually works really well and I recommend it. And that is to create a tiny dipole in the middle and attach wires to the ends. But by creating a tiny dipole in the middle, we define and fix and keep in place the feed point in the center. And then I'm going to do some experimental wave fractal antennas, which is why we showed that video at the beginning. Here's alternative number one, back to the wires page. Look at how I've created a second wire. Both of the wires start where x is 0, y is 0, and z equals 30 feet. And one of them goes out 17 feet, and the other one goes out the other direction 17 feet as a negative number, plus 17 minus 17. Still 34 feet long with the feed point in the middle. See how that works? It's still got 11 segments. I didn't change that. And here's what it looks like. Look at that graph on the left. It looks exactly like you expect it to graph. Just like this. It's the wires are green. The feed point is in the middle where the red circle is, and it's 34 feet up in the air. I run the SWRs on it just like I did before, and there's a graph of them on the right. And look at that SWR. This is at 75 ohms, and the SWR is down to 1.69 back at 13.8, but it's down to near zero, near perfect at the center when I have a 75 ohm feed. The whole thing would be a lot higher, 50 ohm feed. So this is a continuation of what I did with 75 ohm feed. The impedance is 90 ohms, and 90 divided by 75 is going to give you a really low number. Here's alternative number 2. Look at line number 3. I created a dipole that's 2 feet long. 1 foot left and 1 foot right of the center. The feed point is defined as the center. And then lines 1 and 2 are the wires, and they connect 1 foot out running out to 17 and minus 1 foot out running out to minus 17. Same dipole, but I have that little feed point in the center. I really recommend that. It's a little bit of a trick, but the good thing about it is it will give you control over everything that relates to the feed point. You can change the wires all you want to. And there it is. I focused in on it a little bit, but if you look at the picture, you can see the short little dipole in the middle with the green dots defining where its edges are, and the red circle in the middle where it is fed, and wire 1 runs out in one direction, wire 2 runs out the other direction. Exactly like you think it's going to. And look at the right side where the SWR is. In this case, it's still 13.8. The SWR is still the same. The impedance is still the same. And look how wide the proportion of that dipole is. We can't go down to 13.8, we can't go to 14.5, but here's the entire center of the band below 1.5 SWR, which is a great thing. Now, let's go back to off-center fed dipoles. You know I like off-center fed dipoles. I did a program about them. I use that little short dipole in the middle, still wire number 3, and that off-center fed that I like to model and I actually use here at the shack is 41 feet on one side and 27 feet on the other. So starting at 1 foot, we're going out 41 feet in one direction, out to minus 27 in the other direction. Same off-center fed dipole, and there it is. You can see it looks just like it ought to look. On this one, just because it shows up so well, let me point out that on the 2 wires, wire number 1, but especially visible on wire number 2, you can see little red dots, which is all those segments where the current is calculated. You can't have too many of them. You don't have to have a lot of them on a dipole, but the more you have, the more possible it is to feed at a point other than the center. But it's always going to force you to put a feed point on a segment, which is why we started with an odd number. And if you wanted to take and put an inductive load, for instance, on a dipole, because you wanted to have a shortened dipole, you would have to put it at a segment. So it's good to have a lot of segments. It slows down the calculation, but this doesn't take very long at all. And there's where the segments are. You can see them on wire number 2 because it shows up really well. Now, what do you suppose that is? I was up to New York at the beginning of September because my wife and I went up for the US Open tennis. It happens in Queens. And we have a daughter who lives in Staten Island. We stayed with her. And I have a friend, a CW operator's friend, Eric Rosen, KR2AA. And I went over to visit Eric, and we started talking about antennas, and he had made this little monster. And I didn't really understand what it was. I'm not sure I entirely yet understand what it was. But I did a very coarse measurement on it, and it is 2 meters long all the way around the outside. So I think this is a full wave loop for 2 meters. And because it's segmented and have all these other shortened elements in between, that this becomes very, very broadly frequency responsive. And you could also go to 1¼ meters, 220 megacycles, or you could go up to 70 centimeters, where we have a repeater band, and maybe higher. But we started talking about fractal antennas because of this. And he was very interested, and I started studying up on it before I came home from my trip to New York. And I just think it's very interesting. It would have been fun to put this on some kind of a measuring meter and see what it could do, because if you look at the lower left-hand corner, you can see a little piece of coax and a connector there. You could put power on this thing with your antenna measuring device and see what it will do. But I got ambitious, started reading about dipoles, started watching some stuff online about fractals. Excuse me. Came across that video that Yulia stars in, that you saw before. And I decided to give myself a project. And the project to make a 40-meter dipole that is shorter than a full-sized 40-meter dipole. Full-size 40-meter dipole is about 67 or 68 feet long. But if I used some fractals and some thoughts about that and introduce them to the elements of the dipole, maybe I could make this thing shorter. And so I made this model here. This model has 19 wires on that wires page. And it has the shortened dipole in the middle. You can see it there. And it comes down in little 3 foot, 3 foot over, 3 foot across, 3 foot more, 3 foot more. And I tried to use up all the wire. And what I discovered with this is that you can make this. This is 38.5 feet long. It plays as a full-size 40-meter dipole. And what's odd about it, but not so odd once I really thought about it and discovered it, is the elements of this that are parallel have a capacitive reactance to each other. And so I had to make this thing out of more than 68 feet of wire. This is actually using 77 feet of wire to induce an inductive reactance to compensate for the capacitive reactance. But if you lived in a place where you couldn't get a 40-meter dipole up, but you wanted to, you could make one of these things. Perhaps your trees are not in the right place. Perhaps your lot is not small enough is too small to support a full-size 40-meter dipole. Here's a way to get on 40 meters. I haven't actually made one of these, but it modeled really well. And when I think about this, it's the kind of an antenna that probably doesn't stand up to wind very well. On the top horizontal piece where the sections come down, you would need to have a non-conductive tight rope to keep those in place. At the bottom of them, it would probably want to sag into a U shape instead of a squared off shape. But you could take a fiberglass rod that you can buy in stores and a couple of cable ties, and you could try to square out the bottom of this thing. I'm not sure how well it would stand up to winter storms around here, but it will work. I modeled it and it worked. And that's what I got. Look at that. I went to 7.1 megahertz. I chose the segment there, the section at 7.1. You can see where I chose it because there's a green dot on that. It is 1.21 at that spot, at 7.1 megahertz. It's 41 ohms, 41.71 ohms. Divide 50 by 4.71, and you'll get a number very much like 1.21. And there it is. It's not as broadly responsive for frequency as a full-size dipole would be, but if you can't get up a full-size dipole, you could get up one of these. Very interesting. I was concerned about how the mechanics would hold together. So I did another model. I made that one. And that one has little V-shaped pieces coming down, which are a little longer. And you could probably keep them in their V shape by taking a bit of a weight, some fishing line, something like that. Maybe, nothing have to be heavy, maybe an insulator. And you could make it dangle down into a near perfect V shape. It might blow around in the wind some, maybe not as much. Perhaps you took the weight and you put a non-conductive piece of line on it and have it dangle down a few feet below the V. Maybe you could do that one. But here's another form of doing this one. This one's only 15 wires on the model. It's 52 feet long, and it has 75 feet of wire to make it. But look at that one. Look at that SWR, 1.01 at 7.075 megahertz. If you like to run FT8 at 7.074, it doesn't get much better than that. And the SWR is wide enough you could go up and down the band and do all kinds of things like that as well. 49.57 ohms on a 50 ohm cable is near perfect. About as perfect as it gets. Look at that monster. When I was reading up about fractal antennas, I came up with this picture, and I'm not sure what band it's for because it wasn't labeled, but it looks to me as if it is maybe for CB or for 10 meters. And it has a lot of sections in that fractal. I think this is a 10 meter or CB 2-element fractal beam. And look how small it is. If you compare it to the posts that support it, that would hold up a TV antenna, this isn't much bigger than a TV antenna. You could build this. Might drive you a little crazy to do it, but you could build this. Somebody else did. And I suppose they modeled it first before they built it. And look at that. It's on the wires page, I think if I counted right, 278 wires long. That's enough to drive you crazy. And if you hear that they've come here to Franklin, Tennessee and hauled me away in a straitjacket because I lost my mind, this is probably why. If I tried to model this thing. And instead of being like Winnie the Pooh earlier in our hour together, I would be very much like this guy Napoleon the 14th. Those of us who are a certain age can remember the popular music of 1966. There was a popular song by Napoleon the 14th called "They're Coming to Take Me Away, Ha Ha, They're Coming to Take Me Away, Ho Ho." And if they come in here and they take me away, it's because I got too complicated with modeling. But there it is. Model you can do a lot with. It's fun, it's playful, it's free. It's something that you can do for yourself before you build an antenna and found out you could have built it better. If you build an antenna that's too short, you've got to go and you've got to attach wires to it. Putting the pieces together and soldering them together is not going to be as strong as a real piece of wire. So it's good to do your model ahead of time. So that's it. I'm glad you all came today. That's the end of the presentation here at Williamson County ARES in Franklin, Tennessee for the October meeting in 2024, and thanks for watching.